we are doing the centrifuge testing. Of course, first point I'd like to clarify is there is, although we call the ones we looked at yesterday as a static test, centrifuge is always spinning, right? So there is nothing static about those tests either. But what we mean by dynamic centrifuge modeling is that you got on top of the rotation, you need to be able to shake the model while it's still going around. And that's why it is complicated. I don't know if you have seen shake tables in structures lab before. Those are quite complicated, big tables. The largest shake tables are like 5 meters by 5 meters, and uh, to shake them is quite complicated. What we are attempting is to do that while it is going around on a centrifuge. So it is doubly or triply more complicated. But uh, I'll explain how it is done. Firstly, I'd like to say that it's possible to apply dynamic loads. Until now, I've built two, three earthquake actuators. So I've been doing this for a long time. But earthquakes is only one type of dynamic loads. It's interesting because earthquakes do create a lot of damage, but you can also model other things like blast loading, wind loading, and other types of dynamic loading. As an example, one of my PhD students recently was trying to look at HS2, the fast moving train, and we could model that in the centrifuge again. So there are other dynamic loads as well. FE modeling of these problems is possible, but it is quite complex, and you normally require some specialist codes. Only recently, commercial codes like FLAC 2D, FLAC 3D, Plaxis 2D, 3D became available. But until then, almost every research group had their own specialist dynamic code. ICFEEP, for example, the Imperial College one. We use Swandyne, which is developed by Swansea, and so on. There are some advantages and disadvantages of using commercial software like Plaxis, but we'll come to that tomorrow and day after when you get a chance to play with the Plaxis software. Okay. Uh, but most important thing is really the constitutive model that are available. When you're doing dynamic problems, the constitutive model that is there should be able to handle this type of cyclic behavior of the material. Especially for soils, we talked about yesterday that the soil is non-linear and also plastic. It also has this other unfortunate habit of trying to change volume as well. So you can't look at soil behavior just in stress space. So you can, although we traditionally draw more circles are totally in stress space, right? But what is important is what is happening on the third axis, where the void ratio or volume, specific volume, is also changing. So your constitutive model needs to be able to handle that as well. On top of that, you need these non-reflecting boundaries at the end of the mesh, because the real soil is a semi-infinite extent, but you can't make the mesh go occupy the whole world, right? You have to have boundaries. Where you have boundaries, you must make sure none of the stress waves are getting reflected back. That's in fact a problem in centrifuge testing as well, and I'll show you later on in this lecture how we handle that. Typically, I mean, this is a good problem to look at liquefaction of ground. We talked about this yesterday already, so I'm not going to go into the details. Basically, what we are saying is the soil will lose its effective stress almost to zero as the excess pore pressures build up. And the excess pore pressures build up because you're trying to shake the soil. It wants to change its volume, but there's no time for the water within the soil to escape. You can actually do this in the QP dashed plane. I don't know if you use this framework. Uh, I have a pen here somewhere. Huh? Oh, they've taken the pens again. Somebody has the markup in here? शॉप की सर पे वही चला गया. But what we can model in the centrifuge is not, yes, the soil behavior and sand boils and all those things. I even showed you examples of where we could see this in the experiments yesterday. But really, what we are interested in is if there's a building that is constructed on soil like this, we can predict how much it will settle and rotate. Thank you. So you can plot. If that's my Q and this is P dashed is the main confining stress, Q is the deviatoric stress, and the critical state line goes like that. By convention, we draw two lines. So initially, when the soil is just horizontal and before the earthquake, you don't have any Q and you probably have some P dashed. Okay, P dashed is basically sigma 1, sigma 2, sigma 3. These are the principal stresses. So it's basically mean confining stress. And Q is sigma 1 minus sigma 3. You can also put dash, it doesn't make any difference. So initially, my stress rate will be somewhere here. As I try to shear the soil, what it'll do is so the pore pressure is going up, U is going up because P dashed is P total minus U. If U goes up, this comes down. That's why I'm traveling this way. Okay? All is great until I come to here, almost near zero, P dashed and Q. Because I'm hitting the critical state line here, I tend to dilate from here and go up to its critical state up the line, corresponding to its void ratio. And this means that what was coming here has to go in the other direction, and it can only do that if my U is now starts to decrease. In other words, it has to create suction. So this is the soil behavior we expect. There's a framework, and you want to see whether the framework works for the real soil or not. So of course, at many locations, these are the pictures we have taken. This was my former student and current colleague, Professor Haig. At one of the things that happened in Bhuj earthquake was that because it's all salt marshes, run of Kutch, when the sand liquefied, the salt water came to the surface and dried out and left the salt. So we could exactly map how big the sand boils were even 10 days, 20 days after the earthquake. But that sand boils, well, they're interesting. Nobody is actually worried that there's no structure, right? It's all fine. It regained its strength. Nobody worries. But the real problem is things like these are from the Chichi earthquake, 921 Chichi earthquake, where they had a lot of these containers which hold liquid, and this all the soil here liquefied. This is the Taichung harbor, and you can see these cylindrical bulk fluid holding tanks lost their roofs. Why? And this is a very interesting structures problem, because I got a cylinder and with fluid, when I shake it, the cylinder wants to go oval and come back, right? But I got a shell sitting on the top, and the only way I can accommodate this is if my shell pops out. And so people look at this fluid structure interaction as well. Again, I've shown you this many times. We don't need to spend time. But these kind of problems. And that was 1964, the year Professor Agnihotri and I were born. But it keeps going even now, right? This is from Adapazari earthquake, the Turkey earthquake of 1999, and even more recent ones I can show you, where buildings collapse like that. And sometimes in civil engineering, although you have done everything right and constructed your building perfectly, if your neighbor has cut costs, then you will be in trouble because this whole building fell on the other one. So choose your neighbors carefully. Don't settle next to cheaper neighbors. So clearly, these are quite complex problems where we're talking about interaction between the soil and the structure, and also how the soil behavior changes under cyclic loading. Now, dynamic centrifuge modeling offers a realistic chance of recreating these failures at laboratory scale. Now, one of the big advantages of doing centrifuge testing is that we can actually put instruments and see what is happening before the earthquake, during the earthquake, and also after the earthquake, which means we can track the movement of the structure towards failure. And then you can also use this data to validate numerical models. So you got quite a lot of advantages. Before we kind of jump in, I want to cover how actually what is the bit of earthquakes that we want to model. So typically, you can have a problem where you got a building, say, supported on raft and piles. And this is, say, a uniform bed of sand, and I got bedrock at the bottom. When the earthquake happens, you will have a slip, or there are many faults in the earth system, and the fault somewhere deep below will undergo a sudden slide. That's what generates the earthquake. So that slip and the following elastic oscillations are what we see as vibrations. So those travel very quickly through the bedrock. Because bedrock is quite solid, they go very quickly. And every point along the base will see these vibrations. So every point will then start to shake the soil in that direction, and you get the propagation upwards. These are called horizontally polarized shear waves, or SH waves. And these SH waves are the ones which do most damage. You will get a component of P waves as well, but P waves don't have that much energy in them. SH and SV waves are the big ones, but SH is the one because that is the horizontal component we are interested in. Okay, so that is the basic oscillation. Let's do some maths. Suppose I take an element of soil, say somewhere here. I'm going to consider one element of soil there. And I'm going to look at what stresses will it have. So horizontally, let's say I have sigma x, vertically I have sigma y, and I'll also have tau xy on the vertical planes. Yeah. So this is a standard, this is what you would use to draw mosaic, for example. Now, if I consider equilibrium of that soil element, then I can write in the horizontal direction the change of sigma x in the x direction. So delta or dou, partial derivative, delta sigma x over dx. In the other direction, dou tau xy over dou y, plus any force I have in the x direction. Must be, if I add all of them, it should be 0. Then I know my element is in equilibrium horizontally. Similarly, in the vertical direction, dou tau xy by dou x plus dou sigma y by dou y plus y equal to 0. So this big X and big Y are the body forces in X and Y direction. Normally we don't have, we'll have Y, but we don't have any x. Only during earthquake you will get x because of the inertial forces. Now, let's keep this quite simple and say I'm going to, a real earthquake will normally be something like maybe some multi-frequency oscillation like that. Let's get rid of all that complication and say you guys can still see this? Oh, great. Let's say I'm only going to consider a nice sine wave like this. So that is my the input motion. So this kind of motion can be characterized by amplitude A and the frequency is omega. So if then I can write my displacement will be A sine omega t. It's just a harmonic motion, right? And I put minus just to make my maths easy. In other words, what we are saying is I'm not going to do that. I'll start the other way. It doesn't really matter. It's still a sine wave. So if I write my displacement like that, my velocity will be dx by dt. So a omega cos omega t, acceleration differentiate again, a omega squared sine omega t. So far, straightforward, right? So my body forces, in the y direction, I got gravity, g times say rho is the density. So that density times g should give me my vertical body force. Minus just means that it's acting from top to bottom because g is that way. X on the other hand will be this acceleration, yeah, times rho. Rho is the density. So my x is rho a omega squared sine omega t. So I can plug these back and those should be the x and y forces. Now when I want to do centrifuge testing, we want at the model scale, yesterday we said that the acceleration should be increased by n, right? Because you scale the model down by factor of n and therefore the acceleration should be increased by ng, right? Now, I can't say when it comes to centrifugal acceleration, I'll use n, but when it comes to shaking acceleration, I'm not going to do that. That's not right because the acceleration is acceleration, you have to be consistent. So, for the model scale, I need to increase my acceleration by a factor of n. So, n omega squared, n a omega squared, and this sine n omega t. So, this acceleration magnitude is now n times bigger compared to what we had in the prototype scale, as it should be. Then I can get my velocity by integrating that and displacement by integrating velocity, and now I can see my amplitude has come down by factor of n, which is also consistent with our scaling laws. The displacement should all be reduced by factor of n, right? So it is consistent. But to do this, we fiddle something. Can you spot what did I change? If I go back to the previous slide, yeah, frequency was omega t. Here, frequency is n omega t. And this is a bit unfortunate. This is not working in our favor. I can match the acceleration and I can match the displacement perfectly, but I can only do this if I shake my model n times faster than the actual earthquake frequency. This is a very simple way to demonstrate why frequency in the centrifuge test has to be n times bigger, just to make the whole set consistent. So once you do that, we can write a set of scaling laws for the dynamic scaling laws. Until here, we have done yesterday. All these are exactly same as yesterday. Now the displacement, velocity and acceleration. Acceleration is n times, this is also consistent. Frequency is now n times larger, and reciprocal of frequency is time period, so that will be 1 over n. Agreed? Right. So, yeah.
Normally, like earthquake motions will be there, and sinusoidal waves will be doing in the lab. Like, can I make it using any other method, like equivalent to earthquake motion, like that?
Yeah, I need to increase my amplitude of the shaking by factor of n, because acceleration should be n times larger and the time scale should be n times smaller. If I do that, then it will match.
No, not that. Like earthquake motions, like they are not regular.
Oh, yeah. Oh, you mean this? I'll come to that. Okay. We will scale them also the same way. I'll show you in a second. So if you want to model the earthquake problems effectively, we need to subject the centrifuge model in flight while it is spinning to lateral shaking to simulate earthquakes. But then compared to real earthquakes, which have a frequency range typically between 1 to 5 hertz and a duration of 20 to 90 seconds, minute and a half is about most earthquakes. So the scaling laws now mean that, say if I want to do this test at 100 G, I need to shake my model at 100 to 500 hertz. Okay? And the duration, if I wanted to model 20 seconds to 90 seconds, then that will reduce to 200 milliseconds to 900 milliseconds. Pretty fast. Yes. And this is why it is complicated. It also means that once you are applying the earthquake so fast, my instrumentation needs to respond at this high frequency. My data acquisition needs to log, typically we log at about 6 to 10 kilohertz per channel. So everything gets complicated. And this is why it's not so straightforward to do centrifuge testing for earthquake problems. But it has been done. As I said yesterday, there are about 85 centrifuge centers around the world. About 20 to 30 can all do earthquake work as well. Right.
Sir, but for me, more water content is there.
Yes,
But that much of microscope, how it will be?
it will. I'll show you. It will produce the pore pressure because pore pressure is same as stress, right? So it will produce, and the scaling law is 1. So the pore pressure you will get in the centrifuge model will be same as in the field. Exactly the same.
But like permeability, we will be very good. You said like we have to create a particle.
Yes, we will come to permeability separately. Okay. So first difficulty is that we need to shake it fast and log the things quickly. You had a question about the type of input motion earlier, right? Let me answer that first. Now, there are 2 schools of thinking about this. One is we have recordings of past earthquakes. If you go to the PEER, Pacific Earthquake Engineering database, there are past earthquakes, lots of them, records are available. So we can pick the one we want and model, use that to create the earthquakes in the centrifuge. There is another alternative is to use the simple sinusoidal motions. And my professor Andrew Schofield always said we learn more from sinusoidal motion. The reason is when you are applying sinusoidal input motion, it is very clean input. There is one frequency and an amplitude. So you can then see what the soil and the structure are doing in response to that shape. If you put, say, something like the El Centro earthquake or Kobe motion, then that has quite a lot of different frequency components and the amplitude is constantly changing. I'll show some traces to you. Then can we still interpret what's going on to our soil? Well, his argument is you can't, because everything is changing, so it'll be like garbage in and garbage out. Whereas if you put sinusoidal motion, it is all quite clean and you can track if if the natural frequency of the soil is changing, we can track it. So both are true, and many people, even with sophisticated shaking tables, still use sinusoidal motions where you want to study the fundamental behavior. But say you got a structure in San Francisco and you want to make sure that that particular structure with the soil underneath it is not going to get into resonances for maybe 5, 6, 7 types of earthquake motions, you can apply different input motions and show it will all work okay. So both approaches are followed. Depends on what is it that you're trying to do. But one thing I'd like to say is, although we have input motions recorded in the peer database, nobody in the world can tell me at any given site in the world what the next earthquake's frequency content is going to be. At best, seismologists can say, in this area, you can expect magnitude 6 or 6.5 earthquakes. And then you say, two things you should not ask a seismologist: when will the next earthquake happens? They have no idea. Nobody can predict that. The other thing, even worse, is to go and ask them, what frequency content will it have? And they'll say, go home. Okay, so there's no cat and else chance of telling you what the frequency content is. So basically, the future earthquakes are always going to have some unknown frequency content. Amplitude, maybe we can guess, but not the frequency content. So is it not better, because we don't know the frequency anyhow, to use the sinusoidal motions? That seems to be a reasonable argument, and also, since this whole course is about failure mechanisms and how do we understand failure mechanisms and use them for design, for our purposes, if you do the sinusoidal motions, it's so much easier to identify the failure mechanisms. Okay, and I'll show you some example in the lecture after tea. This is the other point you are asking. Magnitude of excess pore pressures generated in the soil during the earthquake should depend on, the amplitude of the pore pressure or the magnitude of the pore pressure should be the same as you would get in the field, because it has scaling law of 1. Pressure has scaling law of 1. However, if the rate of loading changes, will the pore pressure rate at which pore pressure generate changes? Magnitude will be the same, but because we are applying our earthquake faster, will it generate quicker? And we can do this kind of thing, like even in structural dynamics, people actually say that the rate dependent effects are not that big. In soils, especially under earthquake engineering, we assume that the rate dependent effects are not too dominating. But you can prove this kind of thing using FE, for example. But there is one problem we ran into, which is, yesterday, is this power not going to come? At some point, my computer will run out of battery. Anyhow, yesterday we said that for consolidation and all the diffusion based events, our scaling law for time is 1 over. So for consolidation, the time is 1 over n squared. Remember, I was saying it is like time machine and we can model something that will happen in 10 years by running the centrifuge for 9 hours. But we just said that for dynamic events, the time is 1 over n. So this is a problem, clearly fairly big problem. So if I want to model the soil with water in it, saturated soil, then my consolidation will be scaling as 1 over n squared, but my dynamic time or the rate at which the pore pressure builds up will scale as 1 over n. And this is a nightmare because I'll generate the thing too quick and the dissipation will happen too slow. So we need to somehow fix this. What do? We have two options. One is we can change the pore fluid. So instead of using water as the pore fluid, I can use viscous liquids as pore fluids. When I started my PhD, we used to use silicone oil. And silicone oil works well, but it's very expensive. It's actually used in medical applications. More recently, we started using this methyl cellulose. Methyl cellulose is very cheap. It's basically like it's cellulose, so it's like rice powder. So you can mix with water and make the soups thicker. For example, when you have soup, it has a lot of methyl cellulose, so that the soup feels thicker. Okay, so it's edible, so it's non-toxic, and we use that, and we can adjust the viscosity of the fluid by adding more or less powder, and we can get anywhere between 50 to 100 easy. So we will use fluid that is 50 times more viscous, 50 centistokes or 100 centistokes, by mixing it with this methyl cellulose powder. But then you need to prove that if you substituted your pore fluid, then you're not changing the actual constitutive behavior of your soil, because you now said, no, I'm not going to use water, which is the natural fluid. I'm going to use this methyl cellulose, right? So there were people like a fourth-year student called Eaton long time back, and more recently Zheng et al. They basically did cyclic triaxial test by saturating the sand samples with water and also methyl cellulose at different viscosities. And what they have shown is that the stress strain behavior remains unaltered even if you use viscous fluid in it. Okay, so this is the verification. So by now changing the pore fluid, what we have done is the permeability you were mentioning earlier is now reduced by a factor of n, because permeability of soil depends on not just the gaps in between the soil grains, it also depends on the pore fluid. So because we change the pore fluid, the permeability effectively reduced by a factor of n, which means when the pore pressure is building up, say I applied a sinusoidal motion like this, and I'm looking at the pore pressure, it will start and it will do that, and after the earthquake is finished, it will start to dissipate. So the rate at which it dissipates in the post-seismic period and the rate at which it builds up in the co-seismic period will match by doing this pore fluid substitution. Otherwise, the rate of buildup will be too quick and dissipation will be too slow. So we shouldn't be doing that. So a lot of thought has gone in to creating all the bits you need to do this dynamic centrifuge test. It's not just building an actuator, putting soil in it and shaking it. You need to know the theory, and you will get problems and you need to solve the problems. Okay. What other equipment do we need? So for doing dynamic centrifuge tests, we probably need, obviously, shakers. The earthquake actuator or shaker, which is capable of shaking the model in flight. Now, typically, let's say my model container is about a ton with the soil in it. So if I'm at 50 G, the force will be 50 tons and in the radial direction. And if I want to apply something like 0.25 G earthquake on it, I need to hit that with 25 tons in the lateral direction to model 0.25 G, which means that my shaker needs to be able to produce big force. Yeah. And also it has to do it quickly, which means the power requirement is quite high. That's the first point. The second point is the boundary problem. Just like in finite element analysis, where you encounter boundaries, you have to do something special. In the centrifuge also, the model containers are always going to be limited. So the boundaries need to be carefully thought about, and I'll talk about that. And instrumentation obviously should respond quickly. Typically, we use accelerometers. We can measure stress and strain either using PIV or pressure cells and so on. So instrumentation is more or less the same as anything else. As I said, we've done quite a few of these shakers myself. As I said, the biggest thing is that you need huge quantity of energy being delivered in very quick time. That means the power has to be very big. Typically, what are available at the moment, I put here, mechanical actuators. I built a couple of those. Servo-hydraulic shaker, that's the one we are using in Cambridge and elsewhere in the world as well. And this is the one we are trying to build for IIT Bombay at the moment. You can also have electromagnetic shakers. Only Japanese have one or two of those. So the first one I built is the stored angular momentum actuator, what we call SAM actuator, and it is very simple. The whole device we built in Cambridge costed us about less than 20,000 pounds, if you don't count my salary. So it's very easy. All it has is a cheap Italian motor, about 2 kilowatt, and it basically drives flywheels like in your car, and you store the energy in the flywheels, the energy I want for the earthquake. And that bit is very straightforward because I can run the electric motor slowly and build up the energy in the flywheels. The trick really is, and this is what took 6 months of my life, is to develop this fast-acting clutch, bit like in your car again. So the clutch needs to engage the reciprocating rod in less than about 15 milliseconds. And it is not easy, I can tell you that. And once the clutch is engaged, basically it will transfer the reciprocating motion of the rod into the shaking of the box. Because it's so simple, it can work up to G levels of 100 G, no trouble. You can choose the frequency. I'm giving it in prototype scale, anywhere from 1 to 5 hertz. You can choose the size of the earthquake up to 0.4 G, and you can choose the duration of the earthquake. The frequency we can change because I can decide what angular velocity I'm going to run the motor at. So I have an inverter and run the motor to the speed I want. I can have the duration, I can decide how long I want to hold the clutch for on a timer. And magnitude is I can change the offset distance and get earthquakes of different size. This took me about a couple of years to build, but it produced more than 12 PhD students. So it's done very well. And there's nothing wrong with it. We recently decommissioned it because the other actuator has been taken over, but it is really simple and easy to use. And it will produce earthquake motions like this. So finally, here. So this is very clean sine wave motion. It's a mechanical actuator. And if you do the fast Fourier transform of that, you can see it's produced at about 0.8 hertz prototype scale. It got concentrated energy. So sine waves have that nice feature that you can have all the energy at one frequency. And then once you apply this, you can see how your soil model, structure model is changing. What is the frequency response for that? So all it is, as I said, set of flywheels. We oscillate the reciprocating. You run this motor. It's like the old choo-choo train, steam engine, right? So you convert rotary motion into reciprocating motion, and the clutch basically engages the rod. It's very straightforward. And once this is twisted, this twist here makes the table shake back and forth. And because I can adjust the pivoting distance between here and here by using a three-phase motor, I can get earthquakes of different amplitudes as well. That is the cheap and cheerful earthquake actuator. The more expensive version is this one. This is the servo hydraulic shaker. Again, we built it. We bought some critical components, but it's all done in Cambridge engineering department. This can go up to 80 load of about 200 kilograms. And the big party trick this one has is it can do realistic input motions. It can also do sinusoidal motions, but we can also do realistic input motions. And we designed this so that it can receive all the special model containers we designed for SAM actuator can also go on this, so that we are not rebuilding everything. So we built it, and first time, that is the soil model on the ESP box. I'll come to ESP box later. And this is what it can do. It can apply example of Kobe motion, Port Island recording, or it can do Imperial Valley, very high frequencies, and spread out all across. So this is the time trace. This is the fast Fourier transform. So you can see almost at every frequency component, there is some energy. Okay? I'm not saying these are good, but if you want, you can apply. These days, what we do is, we do all our research with sinusoidal motions, but either before or end of our sequence of testing, we'll do one or two of this Kobe motion and Imperial Valley, so that if there are any frequency dependent ones, we also not going to miss it. But we are not going to use this as the main thing. Just for completeness sake, there are electromagnetic shakers. This is in Chiyo University. There's one in Shimizu Corporation in Tokyo as well. And these are basically electromagnetic shakers. I built one for our drum centrifuge, which kind of works, but we never used it in anger. Only fourth year students did their projects on it. Electromagnets are quite nice and easy, but the problem is that to get enough oomph or force to shake it, you need quite a big DC current. And the DC current needs to be of the order of 1000 to 1500 amps. So you need to send that much current through the slip rings onto the centrifuge. And that is really where the Japanese, even they found they couldn't shake big models on that electromagnetic shaker. Otherwise, it is works very easy, and you can buy an electromagnet probably in Jalandhar market. It's they are everywhere, right? Electromagnets are so common, so it's not hard to get it. But on a centrifuge, we need to get the current, basically power, voltage, and current onto them. Okay, the bit I didn't cover so far is the the semi-infinite extent of the soil. This is typically, again, embarrassingly, all these slides are coming from my PhD thesis long time ago. But basically, what you have is if you got a tower, piles, and raft, this is what we are looking at. So we want to do this kind of shaking, but in reality, you have semi-infinite extent. So horizontally, you have no bound. So you expect the soil to run, at least relative to the dimension of the building, you consider that to be plus infinity to minus infinity, right? You must have come across this before. Now, how am I going to create that in a centrifuge model, which is only this long? It's about 700 millimeters long. So at 100 G, it's like 70 meters. But it is a clear boundary, right? So if I make this just like a rigid boundary, when I shake it, the soil inside is going to get slapped by the end walls. It's like, as it moves, you are slapping the soil silly. So we shouldn't do that. So we came up with this idea of having so that is an aluminum ring, rubber, aluminum ring, rubber, aluminum ring, rubber, and so on. And we can adjust the thickness of these rubbers. So what we do in this equivalent shear beam concept model container is I can work out for a given height of soil what the shear deformation in the soil is going to be for a given earthquake. So typically in the first mode, it probably will do something like that, this solid line, right?
You have to simple shear.
Yes, but this is dynamic, right? It's doing both sides. So yeah, in the other half cycle, it goes the other side. Simple shear is only one side. Yeah, a similar idea. So what we are trying to do is to match this curve stepwise. So the aluminum section doesn't deform, but the rubber deforms a lot. So we make the bottom rubber ring quite thick. And as you come to the top, the thickness of the rubber rings gets smaller. So stepwise, we can match the shear deformation, which means that when I'm shaking, the container is also deforming like this, and the soil is also deforming the same way. This is how we can avoid the P wave generation at the ends. That's one idea. This is a tiny model container. So once we made that, we discovered that as the problems go bigger, we need bigger containers. One of the reasons we had to build this is there was some guy, my former colleague and compatriot, called Scott Steedman, and he said that, oh, yeah, soils beyond a certain depth can't liquefy. So he said, mostly in the field, we have evidence of liquefying the soil only the top 15, 20 meters max. And he said, below that you can't liquefy. And I said, that's rubbish. Yeah. So, but I had to prove, right? So we built this one. This models something like 40 meters of soil depth. So if you take the whole of this soil at prototype dimensions, this is 4 times bigger than what E-defense machine can test. So shake tables are therefore cannot handle this kind of large soil volumes. So we showed that liquefaction can, in fact, if you shake it strong enough, it can go all the way to 40 meters. There's no such limit as a depth limited liquefaction. Yes. Yeah. And if stupid people go and say stupid things, codes tend to be the first ones to copy them. So I don't believe in codes. Okay, the other concept we have is this laminar box. This laminar box is effectively like having zero stiffness. So you have each of these as aluminum lamina and they got bearings in between. So when you shake it, the box has no stiffness. So it will basically go wherever the soil wants to go. And I'll show you some examples of use of this laminar box in the afternoon, in the lecture after tea. So it actually, especially for lateral spreading problems, you cannot do those in the ESB box. We had to build this. So a lot of our research is kind of driven by the need. You want to model a problem, what are the limits? Then you go and try and do improve your this thing. So this is also works very, very well. We tried so outside Delhi and elsewhere. A real properly designed landfill should have a clay layer, a geomembrane, base layer, a geomembrane, and it goes onto the other side as well, right? And after the waste is filled, you also have to put a top cover. Now these type of landfills have been built in California, Southern California, since about 1950s. 1950s, okay? And nobody has worried about if I have sand below and if I get an earthquake, I could liquefy the soil and that can lead to uneven settlements. And these things are very sensitive to cracks. It's a clay liner, right? Clay is not great at carrying tension. So it is very easy for it to crack. Then I'm only relying on this geomembrane to hold my leachate or the horrible stuff that forms at the base of the landfill. So first thing was that I had a colleague and friend in Santa Clara University called Suki Singh, and we said, he was working with MSW, and I said, did you think of this? And I said, no, I haven't thought about it. Let's do environmental agency. So this is a new class of problem. Nobody has attempted this, and you can try it, right? We can do centrifuge test. So we create the model and subject it to earthquake shaking, and only the foundation soil can liquefy. This one should not liquefy. The clay liner will not liquefy. It's only driven by displacements. So we created a model. This guy is very good, Tushyantan. And so our centrifuge model was like this. So this is the loose sand which can liquefy. We fill this with model waste and the clay liner. So we had to create model waste, unlike IIT Delhi, where there was a guy who actually went to real landfills and got the waste to characterize it. My students, if I send them to real landfill, they will not come back to the lab. They will leave the program and go somewhere. So we said, no, we'll create a model waste which has the same compressibility and other characteristics as real waste. So we made model waste on this and created the model. This is good 25 years ago. He had like a webcam which is looking here because we're expecting to see liquefaction at the back. So that's the cross section, that's the real model. Very easy to understand. We also had other tests where we were looking at the tension in the geomembrane. So we could see how much is the displacement of this and what is the tension in the geomembrane using some arrangement. And that is the view of the camera looking at the back of the landfill. So we could see the liner movement. So post-earthquake, we could see big cracks develop at the back and the whole thing tilted. The landfill liner fell back and started. So the waste itself we filled with some green fluid so that if it leaks out into the foundation soil, we can see it. So post-test, I mean, this is in-flight picture, obviously. We could see the soil here is now gotten wet because of the pore pressure generated below. The water came up and created these kind of sand boils behind, because we held the water table about here, and so the water coming to the surface means there has been liquefaction. We also had instruments to tell us how much pore pressure we are getting, and also how much is the liner movement. Here the liner was moving, say something like 1.5 to 2 millimeters. 2 millimeters times I think this test was done at 50 G. So it will be about 50 to 70 millimeters of movement, and that's big enough to crack the clay. So you can study real problems like this, and even when things were not uh, previously studied, and uh, when people didn't know there was a problem. So we thought, wow, we got this data. All this work is published in geotextiles and geomembranes and other journals, ASTM for model waste and so on. So we had good set of publications. Then we went to Environmental Protection Agency in Washington and said we had a meeting with them, Suki and me on one side and all these guys on the other side, and said, look guys, you got a problem. All these old landfills may have been subjected to many earthquakes in the past, and they would be leaking. So you really need to go and check for groundwater quality around the old landfills. And then they said, no. Our job as Environmental Protection Agency is, if the landfill owner comes and says, we feel our landfill has leaked, then we will go and investigate. Otherwise, we won't go. And I said, this is stupid. I was also much younger then, and I was very hot under my collar, and said, your job as the Environmental Protection Agency in the US is to protect the citizens. That is your primary job. Why will any landfill operator will come to you and say, oh, maybe the last earthquake created problem for us and all this thing has leaked? They'll never say that, because that's going to cost them money, right? It is so stupid to say, oh, the owner of the landfill should come and ask us. Anyhow, that didn't go down too well. We got no funding from them, but the research is still there. And I'm sure something similar will come up in Delhi and other places when we start to build proper landfills. So at the moment, we are not without proper landfills. Once you start building proper landfills, you also have these kind of earthquake related problems. So we are kind of 2 steps away. So I'm not suggesting any of you will start research in this straight away, but maybe your children should look at that, because we will come there at that time. Okay, I'm going to stop there, and then we'll go back to pile foundations this afternoon. Any questions? Yeah.
Does this surcharge will increase the density of surcharge we have here in
Where?
landfill glass line?
Oh, okay. Yeah, yeah. Basically, yeah. A normal landfill will have, so this is typically about 25 meters. Yeah. And on the top, you pile up another 25 meters or 30 meters. Yeah. So this is the real problem. We are not modeling all of that. So we are only modeling this bit, right? So what we did was that, okay, we filled the waste till here, but I can't make the model come out of the centrifuge container. So we put surcharge on the top to simulate that stress. Okay, using lead shot.
So this surcharge can be applied pre of the earthquake. before earthquake.
Yeah, it's there before the start of the centrifuge. So you get some settlement under the application of surcharge.
So settlements of that.
Yeah, those are all monitored, so we know how much it would settle back. So you can rework the density of the waste. Normally, we don't make silly mistakes like that. Normally, occasionally you may catch me, but the student is very good, so he wouldn't make stuff like that. Okay, any other question? What do you guys think of this whole simulating earthquakes in the centrifuge? When it starts to work in Bombay, I suggest you all go and have a look. It is very exciting when it happens. It's so quick, and the damage you see in the model is quite visual. So it's good fun. Okay, if there are no more questions, we'll stop there, Professor. Small is less than 0.05 G. So it's not going to destroy the model or liquefy it or anything. And then you can see the acceleration at different points in the model. You can see in the loose sand, it amplifies a lot more, the same input motion. And you can do in this case, we also had a structure. Basically, it's like a monopile and a lumped mass on the top. So we want to find the natural frequency of the whole thing. So we can get tower response as well. And you can see my input is so small, but the tower is responding at certain frequency quite strongly. It's like almost 0.2 G, and I'm putting less than 0.05 G, right? So you do pick up the natural frequency quite easily. You also can then look at do the fast Fourier transform or response vector, and you can see what is the input motion I applied and what is the my tower did, and you can see it's massive at that frequency. Therefore, you know that is your resonant frequency. Okay, so this is an example, but we do this routinely for everything. Okay, so what I'm going to do in the next hour, hour and a half, something like that, is to look at the axial behavior and lateral behavior of piles in liquefiable soils. And especially the axial behavior is what is very interesting for this problem. So pile groups in liquefiable soils, there are many different issues with them. Yeah. Uh, for example, it if my pile cap is above the ground surface or resting on the ground, or whether it is embedded, that will make a difference. The amount of embedment also makes a difference. Spacing of the piles makes a difference, and all the depending on the spacing, you can get whether the whole pile group will rotate or it can bend. So is it the flexural stiffness that is important or global rotation that is important? So all these things change depending on spacing of the piles. So, so camp embedment, pile spacing, tip embedment, and pile stiffness. Before I get into this, I want to kind of take you through a thought experiment. Suppose I got a pile cap and say 2 by 2 pile group. Initially, before when we constructed that, when there's no liquefaction or no earthquake, what do we expect? We'll have some end bearing, we'll have some shaft friction, and that is keeping the vertical load in equilibrium, right? So this big downward arrow needs to be balanced by these two and integrated values of the shear stress on all the four piles. During the shaking, liquefaction happens, pore pressures rise, and we know the effective stress comes down, and you will get loss of capacities. You lose bit of your end bearing, your shaft friction probably disappears fully, and that will give rise to settlements. But what we don't know is who's keeping the thing in equilibrium, right? So we know that is a external load that is always going to be there. So somebody needs to oppose that, but we don't know who is doing that. So that's why it's a question mark. After the earthquake is finished and the soil consolidates, we more or less recover what we had here, right? So this one, pre-earthquake and post-earthquake, you will regain some level of pile cap bearing capacity. You got the shaft friction back. You got the end bearing back. Yeah. Oh, earlier I forgot to mention you also will have some level of cap bearing, which in most designs, normally the designer will ignore the pile cap capacity and they'll say that is conservative. Okay, so if I ignore that, otherwise what you have to do is to take the cap area, subtract the areas of the piles themselves, and work out the your normal shallow bearing capacity factor, and say that is going to be addition. And the reason people are not so sure about that is how much load that carries depends on the stiffness of the piles, how much end bearing, how much settlement I got. It's not obvious that all these will be mobilized to the same level. So although my bearing capacity here may be high, I may not mobilize all of it because most of it is being taken by these. Okay, so we know before, we know after, we think, but during the liquefaction event, we don't know. So I had a student called Mark Stringer, who is now a senior lecturer at Christchurch University in New Zealand. And Mark was a game. He used to work for BP, and he got tired of sitting on alone on the offshore jackup rigs, and he said, "I want to come back and do PhD." I said, "Yeah, I have this idea. How do you want to try and do research on this?" So he created this pile group. So the pile groups were, the base had a pore pressure transducer in here. We had gauges all along, but these strain gauges are designed to measure axial loads. They are not meant to measure bending. So we had axial load measurement at 5 locations, and we also had some loads, total load cells on the top. We of course monitor the acceleration of the pile cap and the pile tip and the settlement of the whole pile group. So the first set of experiments he has done is he inserted, so our soil profile is loose sand and dense sand, loose sand overlying dense sand. And this is very realistic because you'll never design these piles to end up in just the loose sand. That is asking for trouble, right? You will always embed them to certain depth. Normally, you work out the effective length you need by using, I think, Bond has one equation, Fleming has another equation that tells you how deep I should go, maybe 5 diameters, pile diameters, or 8 pile diameters into the dense sand. Yeah. So we followed those rules and installed them to that depth. And here are all the load cells, effectively load cells. They're strain gauges, but they're measuring axial load. And S1 and S2 are the wire gauges to measure the settlement. A7 is the accelerations. We measure always the pore pressures and accelerations on either side. Very straightforward. The first set of experiments had the pile cap clear off. So this is my ground level and I have a gap. Normally onshore, you don't do that kind of thing. The pile cap is either on the surface or even embedded into the ground surface. Offshore, many times you leave the pile cap a little bit free because you may not be able to drive the piles to the depth you want it. So it is not totally made up. It is possible, especially offshore, to have situation like this. We wanted to try that and compare with when the pile cap is sitting on the ground. So this I call freestanding, means pile cap is clear of the ground surface. This was all with the before we had the servo hydraulic shaker. So we did all this work using the SAM actuator, which I showed you in the previous lecture. So it creates nice sine waves, right? So it created a sine wave like this. Lots of deliberately we had quite a lot of cycles in this, and these are the loads at the top of the top and bottom of the piles. So SGA and SGA. And you can see that they're getting up in prototype scale about 500 kilonewtons there, and here it is bit less than 500. So the difference between those two should tell me how much is my shaft friction, the shaft capacity. Okay. Before we get and look at the shaft capacities, we also are interested in how is the load being generated. Pile loads are seeing increasing load as the pore pressure dissipates, right? So we had at the so here the cyclic bit is removed and we are only looking at fairly long term. Yeah, these are like 4,000 seconds or something, and you can see the green is a lot bigger than the blue, and blue is at the bottom. Yeah, I think so. Let's go back and check that. Oh, I haven't marked in here. Yeah, I'm pretty sure the one is at the top and one is at the bottom. And as the pore pressure is dissipating post earthquake, we can see these loads are picking up. Yeah. We can also convert this into the QE, the end bearing and the shaft capacities directly because we know the area of the pipe. So clearly during shaking, we lose shaft friction, and as you dissipate the pore pressure, is the shaft friction coming back or not is the thing we are looking at here. Another thing that is important here is the settlement. And here I'm showing you data from two different shakes. Earthquake 1, where I got a massive amount of settlement, nearly 1,000, it's almost a meter and a bit. And the second earthquake, similar size, but second time round, the soil doesn't liquefy as much, and also the pile cap has settled a lot, so it may have come into contact with the ground, right? But what I'd like to see is this is much steeper than this, right? So we had an idea on, suppose instead of stopping the earthquake 1 here, if we continued, what would happen? It would probably have this, this earthquake 2 is basically that, isn't it? We stopped and applied a second earthquake. How is the settlement going to continue? So I need to stack these one after the other. And this is what happens. This is really beautiful. I hope I'll go through it and I'll. Earthquake 1, the settlement stopped here. And if I put the settlement I got in the earthquake 2, it's almost continuing the same thing. There's no field data, no real data like this. And this is one of the nice things about the centrifuge testing. It seems that the settlement curve is a unique curve. And soil remembers what damage you have done last earthquake, and then in the next earthquake it starts from that damaged state and continues. We may have forgotten that there's a previous earthquake, but the soil remembers. This is almost like in consolidation and so on, you say stress history is important, right? Whatever the stress history you subjected to the soil before, it remembers it. And it's true here as well. So it's when Mark plotted this, I couldn't believe my eyes. It is so continuous, the function of settlement. It really stacks well. And after that, he has done on a third earthquake, fourth earthquake. They also stack up as a continuation of that. I'm not showing you that, but basically that is quite a revealing point from soil mechanics point of view. If you ask the structures guys what they'll say, settlement is settlement. By the time you got 1.5 meter of settlement, the pile is dead, the structure is dead. This is not interesting for us. But for geotech people, this is interesting because that tells you something very fundamental about the soil. Yeah. So in successive earthquakes, it remembers. Okay, we've done all that. So we then tried another same pile group in same soil stratigraphy, loose sand, overlying dense sand. Instrumentation location is the same. Only difference is this time the pile cap is in contact with the ground, right? That's the only difference. Now I'm going to compare what you get from the freestanding pile and the pile cap in contact. These are the two cases we were looking at. Pretty much similar level of acceleration. In most liquefaction problems, input motion is actually not that important. Once you hit it anything above 0.1 g, the soil will liquefy. And whether you do like nice swaras in music, right? Or sing different ragas, the soil doesn't really care. It only needs that 0.1 g as a threshold acceleration. After that, it liquefies. You can apply Kobe motions. For liquefaction problems, the input motion shape is not that important. Okay? For dynamic problems, it is, but for liquefaction, it isn't, because the soil liquefies and the structure does what it does. When the pile, in the freestanding pile, I'm starting at about 400 kilonewtons before the earthquake. Then it changes, yeah, and after the earthquake, I'm ending up with slightly lower values. Same at the top of the pile as well as tip of the pile. When the pile cap is in contact, it starts with pretty much the same numbers and it is dropping all the way to 0 in both at the top of the pile and at the bottom of the pile, and then it tries to recover. And this completely blew the mind of Mark, and when he explained this to me, my brain also went on a bit of a fire. What the hell is going on? Why are they so different? The only difference is whether the pile cap is freestanding or resting on the ground. The loads are totally different. And worse than that, these are coming down to 0. This means that the pile is not doing anything. And we said, whoa, this is not what we expected at all, right? So, these are at the top and bottom of the pile, but we also have data for different locations within the pile. And that's what I'm plotting here. So we got at different locations the our axial load measurements using strain gauges. So for a freestanding pile, before the earthquake, I start with 1, yeah, and during the earthquake, it drops to 2, and then after the earthquake, it recovers 3, 4, 5. So 5 is the residual load. So if I look at this, the smallest value it is falling to is about, let's say, 200 kilonewtons. Yeah. When the pile cap is in contact, starts at 1, comes all the way to 2, 3, 4, 5 is the recovery times. This is the post earthquake reconsolidation. And these values are pretty close to 0. I said, what's going on here? Basically, this is the same data as what we have seen before, except now we are plotting the loads along the length of the pile. Yeah? And then the penny has dropped in our head. Basically, if my pile cap is not in contact with ground during this particular earthquake, the total load on the being applied on the pile cap, somebody has to carry it, right? So this I can only come down to 200 because that load has to be carried through all the elevations of the pile. Whereas when the pile cap is in contact, the piles completely don't carry any load. So who's carrying the load? The pile cap, right? So whether the pile cap is free or in contact makes all the difference on the load the pile is going to see. So from equilibrium consideration, this is right because somebody has to support the load. Whereas here I got the pile cap to carry all the load, so the piles are completely unloaded during the yeah.
It's one really good construction practice. Pile cap should be made of
Okay, this is why I was showing about this settlement, right? So if I have my freestanding pile, yeah, freestanding pile group where the cap is away, yes, the piles are carrying 200 kilonewtons in liquefied soil, right? Which means that they will mobilize a lot of settlement. That's the only way it can generate enough resistance to support the load. Whereas the other one, the settlements will be a lot less. And this is quite a revealing set of experiments. So here the settlement will be less, but you are basically relying on pile cap. So what routinely designers are ignoring is what is saving them when this ground liquefies. And there are many examples where routinely, if you have liquefiable soil, you drive piles to go into dense sand below. Even Delhi, Akshardham temple had piles like this. So many examples I can give. So when the earthquake happens, it's the bit they ignored in their design is what is going to save them, which is a bit scary. Because as a designer, you are saying this is not going to be important for me and I'm going to ignore the pile cap capacity. And that is the bit that is actually holding your structure up when the cap is in contact. Otherwise, if it's freestanding, you'll get a lot more settlement. Like 1.5 meters, by which if I got 1.5 meter settlement of pile, my structure is more or less died by that amount of settlement. Yeah.
But what if it is a reverse case? Like pile cap resting on the soil. After first earthquake, the soil is going to sink.
Yeah, and along with the pile.
Not along with the only like if like a pile is socketed in the rock.
In the rock. Then, as I said yesterday, the problem that now becomes a buckling problem. If you, this is the problem with soil, right? In English, there is what is called Murphy's law. This is not real law. Murphy is an Irish guy, and they have a really positive outlook on life. Murphy's law states that if something can go wrong, it will go wrong. I mean, it was obviously a joke that Irish people, it rains 300 days in Ireland out of 365 days. So they are very gloomy. It's always raining and drizzling. So they feel life is always on the down. So this is why the joke is that the Murphy came up with this law saying if something can go wrong, it will go wrong. Okay? So same with these piles. If you rock socket them, they'll try and find the way they can fail. That would be by buckling. If they're freestanding, they will fail by settling. Yeah. If they're sitting on the pile cap is resting on the ground, as long as the pile cap is large enough to mobilize enough capacity, it will not allow so much settlement. But say I made my pile cap quite small compared to say I got 2 by 2 or 3 by 3 pile cap, right? 3 by 3 piles with a cap. And say I got only a tiny amount of net area, then I can't get enough capacity. Then also it will settle, right? So whatever can go wrong will go wrong. That's why I'm quoting the Murphy's law. It's basically the soil is not wedded for one failure mechanism or the other. Whatever is easiest, it will do. And that is the point of these. Okay? So when this PhD work was done, my colleague and famous Professor Malcolm Bolton, he coined this phrase, now you see, now you don't. Okay? Initially you see the piles. During liquefaction, piles disappear, and post consolidation they reappear when the pile cap is sitting on the ground. So this is, have you seen, what is that film? Not Catch Me If You Can. They rob the bank and all that kind of stuff. Anyhow, there's a film where now you see and now you don't. So he applied that to this pile foundation, and it kind of stuck with us. So this is really where centrifuge testing can reveal the load carrying ability of piles and how the load is getting transferred to the soil. If you, now I know this is what's going on, I can design. All I need to do is to make sure that pile cap has enough capacity, right? So maybe make the pile cap half a meter bigger in every direction. I'll have enough capacity. Okay? So these, although we start these experiments for fun, more or less, and let's see what's going on, once you get the data and look at it carefully, and as I said, we went through quite a lot of thinking to go with this. There is also a case where the early version of this data we presented at a conference in Greece, and there was this Japanese guy in the audience, and all he got stuck on was, no, pile caps, the pile settling 1.2 meters unacceptable, and he stood up and walked out of the audience. And my student who was presenting this got very angry, and he said, this 1.2 meter settlement is not, you're obviously not going to design a real pile group to have that kind of settlement. But when you're doing experiments, you can design them to fail. right? But the Japanese guy didn't quite understand what my student was trying to say. Yes, we also know 1.2 meter settlement is too much, but the reason we designed the experiment like that is to get big settlements so that you can clarify the mechanism. So it's not, you don't design experiments always to be not failing and be safe. Sometimes you design the experiment to fail because there's a lot, it doesn't cost us anything, right? There's no building, nobody's getting killed. Yes, the piles settle more. So what? We measure how much they settle and then we understand what's going on. Now we understand what's going on, anybody can design much better. And that's the point. Anyhow. Okay, any questions on the axial capacity? Did you guys find that interesting or not? Very little work is there on axial load carrying capacity of piles in liquefiable soils, by the way. Even my book, this work happened after I wrote my book, so it's not in that book. There's a new book Kenya has published, Amir Kenya has wrote, and I contributed a chapter for that, and we included this in that, this work there, and also published in Canadian Geotechnical Journal. So it's out there, but you need to look for it. Any questions? Pure horizontal. Yeah. Making it incline and all that will make it a lot more complicated. And that's the bit I'm going to talk next. This is after the Christchurch earthquake, and I had a student called Jenny Haskell who looked at lateral spreading, which I'll talk about now. What I want to convey is the excitement of research more than anything else. This is how you can go about, and these are all, we're not doing research for fun. These are real problems and they have real consequences. Yeah.
Sir, actually, it's like normally, like once it is reaching critical state, sorry, the volume remains the same.
Beyond critical state, yeah.
While driving itself, only like if we are going into like adding more vibrations, so soil will be settled.
Not necessarily. When you do pile driving, what you expect is the at the base of the pile or the pile tip, that soil would have reached the critical state, right? In driving, because other you have to fail the soil to get the pile in. Yeah. But there are other things that go around, like, for example, Dave White, we were talking about him earlier. One of the things his PhD was on driving a pile, leaving it for some time, and trying to do a pile load test on it. And what he observed was that the pile load capacity goes up if you leave it for a certain amount of time. And this is normally called set, pile set, or something like that. But is this, the real question in soil mechanics is that just dissipation of pore pressure, and therefore you generate some pore pressure when you drive the pile, and if you allow enough time the pore pressure dissipates, my effective stress recovers, and therefore I can get extra capacity. Is it just that, or is it the fabric of the soil got which got disturbed when you're driving the pile? The grains can reorganize and generate some level of fabric. Now, like always in research, there are people like Dave White who will sit there and say it's all pore pressure because he comes from Cambridge School and we believe that is true. And there are people who do fabric like Mazid Mansari and other people who always say everything in soil is due to fabric change. I don't think we are 100% right. I don't think they are 100% right. The truth is somewhere in between. There is some fabric remolding happening. There's definitely pore pressure dissipation going on. And the set you get is a combination of the two. Okay. So again, research never finishes, right? So somebody can design experiments specifically for that and see, especially if you have carbonate sands, which will crush when you drive the pile, and that's why you get pile runs as well in those type of soils. Then, is it the fabric? Is it the pore pressure? Would be a real interesting research project. Okay. Yeah.
This is the behavior when the pile cap is resting on ground and we are not considering the pile cap capacity in the design.
Yeah, normally that is, I mean, you can talk to many designers, they will ignore it.
Also, like in pile raft design, we include the capacity of that raft in that way. The behavior will be the same.
Now, pile caps are much smaller, and usually you are only using them for maybe 3 by 3 or 2 by 3, that type of pile arrangement, right? To go under the column. Pile raft is a different beast. Pile raft is, you got the raft covering the whole building area and you got piles. The big question there is the load, how much of the load is carried by the piles, and within that how much is end bearing, how much is shaft friction, and how much is carried by the raft. Now, routine design, static design, I also recommend pile raft for many problems, in consultancy problems in Kakinada, for example, where the structural designers who are designing this, they don't understand pile raft foundations. So whenever I say, go do this, they'll say, are you sure? And I say, yeah, I'm pretty sure that's how you do this. The load sharing between the pile cap or the pile raft and the piles is a real interesting one. People like Randolph over years have come up with springs and pile as a spring, the beam on Winkler foundation type of analysis for the raft, and in the end there should be strain compatibility. Basically, if the raft is going to bend, then the pile also need to get pushed down, and you work on that strain compatibility between the pile and the raft. Again, most of the stuff Mark Randolph has done is to do with imagining all this is elastic. Yeah, we know the soil is not elastic. Therefore, there's a lot more work to be done, even for static, which he had a bunch of students and he did quite a lot of work on that. If I were to look at raft foundation with piles in liquefiable soils, that is going to be even more interesting. This is just a precursor for that. So when I get a next bright PhD student, that is in my mind to go and do that. I haven't done it yet, so I can't answer. But you're right. Pile rafts are a different beast, and the load sharing is going to be very interesting. Okay. Okay. So the bit about laterally spreading ground, I'll do the one version of this today, and the rest of it I'll do tomorrow, where we look at the limit equilibrium methods as well. So the problem is piles. Here I'm focusing on pile spacing. Typically, pile spacing is anywhere between 5D to 2.5D. That is the range. You don't normally design 10D spacing. That is almost designing like single piles. 5D is the upper limit. 2.5D spacing is the lower limit. So when Jenny showed up, we thought we'll look at this because as she started her PhD, this Christchurch earthquake happened, and Mishko Kubranowski was interested in this. So cap embedment we dealt with for level grounds. Now we are looking pile spacing. The other ones we will do later. Typically what you expect is that if I have piles and I have a sloping ground coming, trying to spread past the pile. I showed you some field examples from Taiwan earthquake in the last 2 days. You expect passive wedges to form behind the pile, behind the piles. If the spacing is close, these wedges will overlap, right? So the amount of load I'll attract will be less. If the spacing is large, then these wedges are pretty much on their own. So the load I attract on my piles will be big. So that is conventional wisdom. There are also things like if the free field soil is displacing, like with increasing amplitude towards the surface, the soil in between the pile group may move less because the most of the load is being carried by the pile, right? So it will flex. Say if it's a flexible pile, it does something like that. But these displacement vectors will be smaller than this. We don't need centrifuge test. We can guess this is what happens. Also, we talked about formation of these hinges. So we do get the peak bending moments will be somewhere like that, which we looked at yesterday. Effectively, the New Zealand code talks about restraining action and driving action. So the earthquake creates the driving action and the structural stiffness provides the restraint. It's like a frame action, right? Basically a pile group with a pile cap is like a frame. Now this is, I probably showed you this already. Typically this is what we are worried about. The excess pore water pressure will once the earthquake starts, it builds up and stays like that until it starts to dissipate in the post-earthquake period. So I think I showed you this already, this animation, right? So you got initially stiff response, and as the pore pressure builds up, the loops, the tau gamma loops widen up, and as it goes, they become these what they call banana loops, where my tau gamma response is almost like flat, but at extremes, I get dilation to create this stiff response. But most of the strain range, you get very soft response. Right. So we wanted to model this in the laminar box. I needed the laminar box because when I shake this, the soil wants to move from upslope to downslope. So if my ends are even ESB model container ends, while they match the shaking, they can't deform with the soil. So laminar box is required for this kind of lateral spreading problems. So also we mount this, we make the model horizontally and we put on a wedge, either 3-degree slope or 6-degree slope, and you mount them on wedges. This is what we do for other tests as well, which I'm going to talk about tomorrow, Nappett's test, but that's basically. And then you drive the pile. This is obviously the 2D spacing pile. And then you put on the centrifuge and you do the test. And then post-test you can also excavate and see where this ended up. So you got some base layer, which is dense sand, and the liquefiable layer. In this case, our pile cap is always embedded into the soil. Okay? So we are not worried about the settlement issues like what I've shown you earlier. So when I shake at the end of it, it will do that. Okay? So this is an animation she created, but I can show you pictures afterwards. Basically, each of these rings can slide on the next one, which means if the soil wants to go there, this will simply follow it. This is a cool video. This is the plan view, and this is the first time we had high-speed camera. So this camera is taking 1000 frames a second. So although I'm shaking it quite fast, I can still capture and see what happens during the shaking. So that's the plan view. The 4 piles are going in, yeah, and this is sorry. So the slope is high there and down there. So we expect the slope to move in this direction. Yeah. So I hope this plays. Okay, so that is what has happened. So you can now see that this whole pile group started there and moved. I'll replay it again and you can mark the initial position. So it's there, right? And after all the cycles of the earthquake, it has ended up here, right? We can see also the soil that is coming here is being stopped by the piles. So these squares don't deform, whereas these started to shear on the sides of the pile. So just having squares, we can see where the strains are. Okay, then we can look at the data itself. So that is visually good, but what you really want is the look at the data. So this is all in dense sand, so nothing much happens. Yeah, in the loose sand, I'm looking at the pore pressures. You start getting big no, acceleration. Sorry, my mistake. Input acceleration within the dense sand, nothing happens, but in the loose sand, you get these big spikes. Yeah, and at the surface, the whole amplitude drops off because if the soil turned into liquid, accelerations cannot go up, which means the top layer will get isolated. But why are these things so big? Is the question. And that is because of the thing I've shown you this morning. When I'm at zero stress state, if I try to shear the soil, it will have to go along the critical state line and therefore it has to create a lot of suction. If it creates a lot of suction, the soil temporarily stiffens and therefore it can pass big acceleration. This phenomena was named by Bruce Cutter and I think a guy called Gudgeon as deliquefaction shocks. It's basically a shock wave going through the soil because the soil which is like liquefied for a fraction of a second turns into very stiff material and then it softens again. So whenever it is turning into stiff material, I can carry this shock wave. So the physical data you get actually has a lot of meaning associated. And the same thing happens, I'm sure, in reality as well. Now we can also take a little time frame in here, like a yellow box, and this yellow box is plotted here. So I'm only seeing few cycles. Then I can, if I draw a vertical line, I can see the delay in the propagation of the shear waves clearly. So that is the phase lag I'm getting as the shear waves go from top to bottom to top. So there's a lot of information you get, which means if I know the delay, I can work out shear wave velocity. If I can work out shear wave velocity, I can work out what the reduced shear modulus is. All that information is coming straight from the accelerometers. Pore pressures in the dense sand, I get maybe 60 kPa excess pore pressure. But if you work out to liquefy the soil, I need about 80. So this dense sand hasn't quite liquefied. As I go to the top, I can see I'm crossing the liquefaction line. So we know the shallow layers, the slope layers are all liquefied. Now, earlier I said that we are getting this deliquefaction shocks. That is confirmed here because the pore pressure is not just going up. In every cycle, it is dilating, yeah, or it wants to dilate, and you get suction. And I can see the suction. So that is, say, 35. I'm getting a suction of about 15-20 kPa. And it's even more there relative to the shallow depth it is. So that's why the soil is locking on us. So we see the acceleration response, but also confirm that with poor pressure response. Okay? So this all fits together. Great. This is what doing experiments is all about. But really, we are trying to answer a design problem, right? So here the piles are also gauged with strain gauges, so we can measure the bending moment. So I got 5D spacing and 2D spacing, and this is the upslope pile and that is the downslope pile, right? So basically what we are saying is, and the slope angle is 3 to 6 degrees in different experiments. Okay, so this is my upslope pile and this is the downslope. So we are looking at the bending moments in these. Yeah. So at the base, obviously the bending moment has to be 0 at the tip of the pile, and we get a shape. If I plot these bending moments at a particular instant, a shape like that. And the downslope one, this is about, let's say, 300 kilonewton meter, and here it is about 500 kilonewton meter. Yeah. So clearly the upslope and downslope are not carrying the same bending moment. When the spacing is reduced, base and also the top are almost 0. And I'm getting a different shape, right? So this one is a double curvature like this, and that is simply one same shape both for upslope and downslope, and also they're not that different. Why is this? The only thing we changed is the spacing. Yeah? What is it trying to tell us? Sorry? No, pile cap is embedded for both cases. It's only spacing that is different, right? Yes. Yeah, but the 5D spacing means I'll generate individual wedges according to what I said before, right? Actually, it is to do with the mechanism, right? When the spacing is big, if I draw the plan view, the soil is able to flow like that. If the spacing is less, the soil does that. Oh, sorry. You can do that. So if the spacing is less, it's almost working like a one large diameter pipe. Whereas these ones, it can go around the upslope and downslope, the top and bottom pile separately. Which means in one case, the whole pile group will simply rotate. If it does that, the bending moments will be small. If I have more spacing, then the piles will have to bend like that, right? That creates a lot more double curvature and bigger bending moments. Simply by changing spacing, we are changing the failure mechanism. So closely spaced piles will act as one large diameter pile. Great. but they also are vulnerable to rotation. Whereas widely spaced piles more or less act as individual piles. This type of thing doesn't happen in static loading. Spacing means what happens if you look at Piglet or Randolph's work, what they say is that the amount of interaction between upslope and downslope piles will change. That's all that will happen. The whole mechanism doesn't change for them because the soil is never going soft. For us, the soil is kind of turning into mush, which means the failure mechanism can change. So this is the beauty of earthquakes and dynamics. We actually change the failure mechanism because the soil is able to. And you can't have the same for static cases. So getting the data plotting like this is one thing, but to delve more into it and get the essence of that out, for that we need to understand the failure mechanisms, and hence the title of the course. You cannot do this, you can't look at the dynamic loading on piles without knowing failure mechanisms. You can have a go, but you'll make quite big blunders if you do that. So this is the displacement for the large diameter and small diameter. You can see this one is trying to bend, whereas that whole thing simply rotated. So we did post-test site investigation to get the deformed shape as well. So we got data, we got the pre and post test configurations, and so we really need further guidance for piles in laterally spreading soil, especially when they're in pile groups. Spacing, I mean, we've done the two extreme spacing, right? Where does the bending translate into rotation? People can do more experiments between 5D and 2D, maybe 3D, 2.5D. We haven't done all that. You kind of pick the lowest hanging fruit and say, look, that is interesting, and move on to another problem. But to convert that into design guidance, I need more PhD students who can do those in between tests as well. And one of the problems in Cambridge is we are always having exciting new problems. We never go back and fill the gaps. Okay, that's all I wanted to say. Any questions you have? Yeah.
I'm very much curious to know how you have maintained the density experimentally. How you have maintained these less dense soil at the top and more dense at the bottom.
Like all these things, I spent way too long in the lab compared to my family when they were growing up, particularly. We built an automatic sand pourer which will actually pour the sand. You can bale, it basically controls the flow rate of sand and also the height of drop. Just like a 3D printer, it goes and pours the sand, and you can choose the height of drop and the rate of flow of sand, and it will make dense and loose sands. So there's a machine to do that. It's like a 3D printer.
So you use the mesh, means different size of mesh for
Yeah, the hopper has a little wire mesh on it, and there are papers where we wrote about how do you calibrate it to get a particular density. But it's been in use for the last 20 years now. The current students simply know what they do calibration first in set volume cylinders, and they know exactly what density they'll get. And you weigh the model before and after, you know how much sand you poured, so you know the volume, you confirm you got the density as well. On top of that, these days we also push a in-flight CPT to confirm that the loose sand, where the dense sand is coming, where the increase in CPT resistance counts all that is there. A lot happens. I'm not showing everything, otherwise, I'll be here for 3 weeks. Even saturating the models with methyl cellulose, it's all a computer controlled process. There's a thing we developed called CAMSAT, so which keeps the flow rate small enough so that you don't fluidize the sand and slowly lets the fluid. It takes about 8 to 12 hours to saturate these models because you're trying to saturate them with 50, 100 centistroke fluid, right? So it's going to take a long time. When I was a student, we were doing it manually, and I would stay all night long in the lab. And I thought, this is ridiculous. So we built a machine that will do that. So, yeah, we improve slowly. Okay, anything else?
There is something called sharding with file groups. So, how does that affect spacing? Sharding, like like files in upslope and downslope.
Yeah,
Because of the files in downslope, there is effect on the downstream.
yeah.
So bending moment changes. I mean, like there is an effect. So, is there any effect with spacing?
Yeah, that's what we're talking about, right?
No, I mean, like, how does that affect?
Not as much as in the static loading. Because you're resetting the stiffness of the soil, in static, say, slope is there, and you apply lateral load, the upslope piles take a lot more load than the downslope piles because most of them are the ones which are opposing the movement, right? And that's what you're calling. And this is all done by Randolph a long time ago. What we have here is initially we thought that is what is going to happen, and then discovered actually no, because once the shaking starts, the soil stiffness is getting reset. So you don't get the same level of protection for the downslope pile. More than that, the global rotation mechanism taken over. So when we reduce the spacing, then because all the piles are connected through the pile cap, it's easy for it to rotate. And the whole bending moment has gone down in all piles. So that's why these liquefaction problems are interesting. You're starting with soil that is stiff and you're resetting. Yeah? Okay. Anything else?
Sir,
Yeah?
how do we replicate earthquake in centrifuge test? I am unable to understand. How do we replicate earthquake in centrifuge test?
Did you miss the lecture before?
Sir, I was unable to understand.
Okay. You are trying to create a shake table which will shake the model in flight. And that's what I thought I covered in the lecture before. Yeah, there are these things we built which will fly on the centrifuge, and when we want, it'll shake the model. Okay, it's like a big actuator. Okay. Anything else? Right. I believe you were all set a couple of questions to solve yesterday. Where are the solutions? This is all on Professor Agnihotri's assessment of CRR and CSR and also the settlements, right? I was quite interested to know the answer. I gave you data for SPT and CPT at the same site. Which is good, which is bad? Are you getting the same settlement estimates or not?
Across safeties were similar.
Yes, but settlement is what I am interested in. How many of you have done? You're here for 5 days to do this, right? So what else is, I mean, we are lecturing what, 3-4 hours a day? No more? Now is your time to do these things properly. Okay, because you haven't done that, I'm going to set you one more. Copy this, and I want the answer for this tomorrow as well. I'm going to make this up. Okay, first one is this half a meter diameter pile, 10 meters getting rock socketed. It got some load on the top. So work out the buckling load. Okay, so you need obviously to work out what the E of concrete is, I of concrete is, and so on. Yeah, and then see. The next one I want is same soil, same piles, but this time you got. So what you want to work out is for the pile group and the single pile, what is the peak rate per pile, and explain why if they're different and why. Okay, work those out and show it to me tomorrow. Otherwise, I won't be pleased. Rock socketed, as shown. Okay, we'll stop there. Okay, sir. So afternoon, 2 o'clock. Maybe today we will focus on what you learned so far and see what calculations we can do. And tomorrow and Friday, you're going to try and use the FLAC, right? Sorry, Plaxis, right? So we need to set up a problem that you can analyze that. Huh?
We will also explain.
Abacus. Yeah, but for seismic problems, Plaxis works, right? So you probably want uh, the Plaxis. You need to think about that.
Better to concentrate on one.
Huh?
Better to concentrate on classes.
Plaxis, yeah, that's the. But I don't know whether they have the dynamic bit and the Manzari model in it. Because it depends what components they purchased with Plaxis.
Actually, sir, our practice license that is expired. What is the problem? You mentioned N2 come. Yes.
Okay, so in that case, we can do like a. Abacus is a 3D. So if you can create the pile and the soil in it, and by changing the head load, it'll change the inertial load being applied, and we want to get the bending moments in the pile for different load application. Okay, so that would give them an indication of inertial loading coming onto the pile. Right.
It is important because we are not having a matic license at the moment. So it is important that we not to do.
Oh, you mean for Praxis? Yeah, yeah, yeah. They'll come after you. Okay, so but for this afternoon, what we thought you could do is uh, day before yesterday we gave you the Sudan data from the Sudan site, right? So that has different lithographic units. I think up to about 20 meters, 15 meters. and you have the CPT data, right? For this. So use the CPT data, and first thing I want you to do is to say, if I have a pile going like this, yeah, so I'm going to apply 25 kilonewton load. That's like 2.5 tons on pile diameter of 300. So what we want to know is what's the pile capacity? Yeah, using the CPT data, how do you estimate it? And so what is QP and what is the uh, once you get this, you can work out the factor of safety, because this is the estimated capacity. We're applying 25 kilonewtons. You should know what is the margin of factor of safety. Yeah. Now, the other thing is, you also estimated for this problem that this soil will liquefy and settle, right? So, what will happen then? So, post earthquake, so this is all static core pre earthquake, right? But post earthquake, maybe up to immediately you got how much? About 300 millimeters of the soil layer, right? So the soil itself is going to settle, but the pile is going to stand proud. So if that happens, what extra load will come onto the pile? The soil wants to settle, pile doesn't want to settle. So what is the new factor of safety? Do you understand the problem?
Below 2P what? Below 2P what?
A row settlement of the pile. Yeah. So if you calculate the settlement of the pile, if that is less than 300 millimeters, that's when negative skin friction will come. If it is more than that, obviously it is settling more than the soil, therefore you will get positive skin friction. Yeah? You will get positive skin friction. Yeah? So that's the calculation. So if all of you have done the first set of calculations like I have asked, we are building on that, right? Because that is just for the soil. Now you are doing it for the pile inside the same soil. So it's important that you do the homework that is sent. But anyhow, this you're going to sit down and everybody has piece of pen, paper, calculator, that kind of thing. Yeah? Get on with it then. If you're not sure, I'm here, Professor Agnihotri is here. Come and ask us. soil has been provided. This one. Yeah, we are doing it like a static type. We are adding honeydew solution. This one is small. This is going to add the other way. If you do that, this number should come down. This is a little static. Yes. That is not. This is not going to be it's very 4 layers, 3 layers. Is all about us doing business. We can't calculate everything. Doesn't matter. But here for what's that new place yesterday? Is it giving me the procedure? Okay. You were good? That's a very quick calculation, but it tells you what is going to make it. Yeah. That's what we do. Yeah. All right. Two. Okay. And when you apply the down track, you can use the same QC values but because the soil is now pulling it down, use right instead of adding it, it's going to reduce some factors. Then your factors are going to come down. Soil around it, then the factor of safety should come down. Because the down drag is adding as an extra load on the shaft, and you lost the shaft capacity, therefore your factor of safety should come down quite significantly. And some of you showed me numbers of close to 1, which means the pile has a risk of failure. Okay? So it's what should have happened. Anyway, do finish the calculations. Also, do the buckling calculation for tomorrow. We'll take it, we'll start again tomorrow. Is it 9:30 or 10?
schedule is 9:30, but now they are doing.
That depends on the day. Yes. Okay. Yeah, that is probably okay. Okay? See you tomorrow.